Hello, everyone. My name is Roman Bishop. I'm currently a senior undergraduate student at Florida State University in Dr. Kennemur's polymer chemistry class. And my polymer to research for my presentation is PVC, polyvinyl chloride. This is a super common plastic we all see a lot in our daily lives. I'm happy to show you guys the backstory, how it's made, and all about it. So, quick history of it. So, two researchers in Europe accidentally discovered it back in the 19th century. First, it was French physicist Henri Regnault back in 1838, and then German chemist Eugene Baumann in 1872. Um, as you all probably know, PVC is a white polymer that's usually pretty rigid and thick and hard to deal with. So if you imagine some of these researchers back in the 19th century, once they were able to form this polymer in their flasks, it was pretty hard to play with or mess around with because once it's made, they didn't really know how to mold it or form it, do really anything with it. So they would kind of just throw it away. But they made it accidentally from vinyl chloride gas exposed to sunlight and some photopolymerization methods. Um, and then obviously this is before the Industrial Revolution really kicked in. So commercial applications weren't really mastered yet. Because it was just so durable and hard to work with, they didn't really know what to do with it just yet. But fortunately, in the early 20th century, German chemist August Klott patented PVC in 1913. He kind of figured out some better ways to use it. And then American chemist Waldo Semin, I believe is how you pronounce that last name. Pretty unfortunate last name, if you ask me. But the B.F. Goodrich Tire Company was contracted to create a lot of goods for World War One, and then they kind of kept that up and trying to make new polymers, and so they hired this Waldo guy to try and make a replacement for natural rubber because natural rubber comes from a plant that is not really abundant at all and kind of hard to replicate. So they tried to find a synthetic way to create rubber, and Dr. Waldo Semin made a pretty good way to do that. It was an American chemist, and PVC was initially used as a water-resistant coating for fabrics, and the commercial production really kicked in 1933. And then, fortunately, Waldo Semin didn't just stop at PVC; he created a bunch of other synthetic plastics. And then obviously with the Industrial Revolution already kicked in the 1930s, they were able to commercialize a bunch of different uses for it. And so, yeah, so PVC, obviously right now in the modern day, and really for the past 80 years, 60, 70, 80 years, those common uses of PVC have been pipes and pipe fittings, flooring, like linoleum flooring, roofing and ceiling structures are very commonly made out of PVC. Power and telecommunication wiring, like my computer cord right here, and any charging cable, that's usually going to be coated with PVC. And then window and door linings, those white plastic linings you'll see, that's also made out of PVC. And the reason they're used so much, PVC is used so much, is it's just extremely durable. I mean, it has a very high resistance to water, light, corrosion, and darn near every chemical. I mean, it's very resistant to most acids and bases. It's really hard to just dissolve it away, and it doesn't really burn that well either. And that's why it's just so widely used. It's very easy to make. It's very durable, and I guarantee you, every single one of us encounters PVC. Every time you plug in your phone, every time you plug in an appliance, every time you look at a window, PVC is everywhere. Oh, but I do want to mention the one chemical that PVC is not resistant to is aromatic hydrocarbons. Um, and we'll get to the chemistry on that in a little bit. Um, but yeah, so the European chemical company Vinyl Plus claims that they're able to recycle 6.5 million metric tons of PVC in the past 20 plus years, which is pretty good. I mean, it is a very durable plastic, but once you grind it up into a fine powder, it's easier to remelt it and remold it and use it for whatever new purpose you want to use it for. And you guys can pause this video if you want to zoom into this graphic, which is actually a pretty cool graphic to look at. And then the link on the right side will show you more cool graphics from this European company. And then, yeah, here's just some more numbers. This just shows the exact like physical and mechanical durability numbers of PVC. Again, you could pause the video if you want to look at this more in depth. Um, I get, for example, it shows the like flex strength of PVC by PSI if you try to like bend it or break it. Um, and yeah, just in cool numbers of PVC. That goes to show how durable it is. And then on the simple bar chart on the right, it just shows how much PVC is being made each year. So in 2018, it was 43.3 million metric tons. And then in 2 years, in 2025, um, many people are projecting it to get near 60 million metric tons produced worldwide. So creating PVC is much different than what it was back in the 19th century. These chemists just, finding it in their flask after exposing vinyl chloride gas to light and then not really knowing what to do with it. Obviously, we know industry has clearly got this down to a science. So there's really just three main steps of it: converting ethene to 1,2-dichloroethane, producing chloroethene from 1,2-dichloroethane, and then polymerization of the polyvinyl chloride itself. And so um, the biggest part of it is cracking ethane because vinyl chloride isn't just available really commonly, so you kind of have to synthesize it from ethane, propane, naphtha, and some gas oil. And so if you combine the ethene and chlorine with an iron chloride catalyst, it is a very thermodynamically favorable reaction. As you can see, it's gives out 178 kilojoules per mole. And then the 1,2-dichloroethane is then used in the next process. But if you look on the little chart on the right, this diagram shows a fluid bed reactor for the oxychlorination of ethene to chloroethene. Just a really cool graph to look at. And then we have so producing more chloroethene from the 1,2-dichloroethane. If you just heat it up, you're able to kind of heat out hydrochloric gas, which obviously we don't want. We do not want to reduce hydrochloric gas to the environment. It's very dangerous. We don't want to just produce a strong acid gas and have it condense into a liquid and just release that to the environment. That is not very good. So fortunately, if you just recycle that back, the hydrogen chloride back with oxygen, you can use that in this previous oxychlorination step and convert the hydrogen chloride to chlorine gas and just keep the cycle going. And yeah, it's cracked at 650 Kelvin, pretty hot temperature. And then, yeah, it's not really just, step A, B, C, and then we're done. It's more of like a loop with 1,2-dichloroethane as a product, as our final product we want. Because the byproduct HCl we don't want, and we can go back and use that for something else. So yeah, I drew out a free radical polymerization arrow pushing mechanism over here, which is an easier way to see it. And then the initiator is usually an organic peroxide because it's soluble in chloroethene. But AIBN also works. That's one of the initiators we've been discussing in class. But yeah, if you just use chloroethene at a high temperature and high pressure with one of these initiators, you're able to create polychloroethene, which is polyvinyl chloride. And yeah, it's just a free radical polymerization is the main mechanism. So yeah, I mean, as I mentioned earlier, you're going to see every time you plug your phone in and have it charged, you're going to see polyvinyl chloride. And if you're wondering how you have these very rigid PVC pipes and then these loose PVC cables you use to plug your phone in, that's because a lot of additives can be added to PVC. So some of the additives can be used for different reasons. You can add it to make it more flexible, like phone cables. You can add additives to change the color. Like some of the additives they use to change the color are zinc oxide and zinc sulfide. And then I'm not going to list all of them because there's a ton of additives, but some of the additives they'll use to make it PVC more flexible. You got dioctyl adipate (DOA), trioctyl trimeltate (TOTM), dioctyl sabacate (DOS). Just a lot of different additives you can use, and that's the source right there. And then you can also add some flame retardant additives to PVC as well. Um, these include decabromodiphenyl ethane, DBDPE, and then zinc borate also works as a good flame retardant. So yeah, a bunch of different additives you can use for PVC for a wide range of uses. And so the reason PVC is so durable is because it's atactic. And so if you look at this diagram on the right, um, when you're polymerizing this substance, it's not just a simple, oh, we're going to have chlorine in this conformation every single time. It really is um, just totally random. I mean, it's these chlorine atoms have a random conformation every time they add together. So which makes this random conformation very difficult for adjacent chains to lie close together cleanly, which makes it very similar to glass, because glass is atactic on a molecular level as well. But this is why it is mostly amorphous, and it's pretty much impossible to get um, a PVC crystal because you would have to find a way to control the tacticity of this polymerization. And fortunately, this is actually what helps it resist oxidation, which is why it's able to last so long. And yeah, I mean, as you can see, the atactic is, it's totally random. I mean, it's impossible to really pick and choose how to choose that conformation of chlorine. So even though it is an extremely durable plastic, it is possible to recycle it. I mean, you just got to grind it, clean it, purify it, and then remelt it and remold it. Fortunately, when you grind it into a fine powder, it is easier to melt at higher temperatures. And right now, we don't know the exact lifespan of basic polyvinyl chloride, mainly because the mainstream use was started in the 60s, and even the PVC pipes created then still haven't degraded yet. So even though these pipes are 60, 70 plus years old, they're still in pretty good shape. So really, if we're just looking to find the lifespan of PVC in ambient conditions, we just have to wait. It's really all we got to do. But yeah, fortunately, it is very recyclable, and this does reduce the need to extract carbon from the ground. Um, just for these previous like ethene, hydrocarbons that from oil, we don't really need to don't really need to get more of those because we can just recycle it. Oh, what the? Okay, I don't know what my computer just did. Don't know what my computer just did. Okay, but um, but yeah, it helps reduce our carbon footprint, so that's pretty cool. And so a lot of the stuff that it gets recycled into, like anatomical skeletal models, toys, and then other random plastic objects are also what it gets recycled into. Um, but yeah, so that's it. That's PVC. I'm sure you see it a lot in your daily life, and here you know a little bit more about it. How do I?